Hi everybody, we're back today. I finally got my components in for the continuation of this Series 20 M22 Pioneer amplifier, and I'm ready to start digging into it. So in this video, all I'm going to do is we're just going to go through and kind of look at the insides of it, how it's built and so forth. I'll replace some of the capacitors, and then at the end we'll put it through the test. We'll play some music and we'll do some testing on power output. We did a preliminary one in the last video. We'll dig into it a little bit better, look at the distortion, some things like that, and then we'll wrap it up and be on to our next project. So if that sounds interesting, stay tuned. Okay, so I have this thing flipped upside down on the bench. Let's get the screws out and see what it looks like inside. And there it is with the covers off. Boy, isn't it beautiful the way it's laid out. It's a work of art. I really love the way this thing's built. And look how sturdy. I mean, this is all metal. So here's your 3 relays. This is the soft start in the middle. These 2 are your speaker protect relays. Hopefully they'll all be good and they won't need to be replaced. That the terminals won't be tarnished or anything. By the way the amp performed when we were testing it, I really don't think these are bad. They're probably in perfect condition. There's right and left channel modules here, and they're actually different. You know, in a lot of amplifiers, the right and left channel amplifier modules are the same, or they may be mirrored but the same circuitry on them. These are a little different. You have like the power supply is also part of one of the boards, and there's other circuits on the other boards, so they're different. And we're going to see that when we get this apart. Very easy to take apart, and then we'll have to clean in here a little bit. You have 4 screws, and the whole amp module drops out. And all we have to do is unplug a couple of the connectors here, and we'll be good to go. So let me get those all out, and we'll get the first module out. Let's start with the harder one. I think this one will be more difficult because this one has all the power supplies and things on it. So let's do that one first. All right, so let's see here. Get something to clean this off a little bit. And there's our first amplifier board. The rectifiers are on this one, and you can see there's a lot of that tarnish on the leads of the diodes. You can see, you can tell that it's that tarnish when it just comes right off like that. It comes off on your hand. You can see. So I can clean those ones up, and I notice one of the transistors has it. This one here, you can kind of see right in there, has that creeping doom. So this is going to get replaced. 2SA 628. Okay, we can replace that. Here's your differential input transistors right here. And these, even though these ones are working perfectly, I will most likely replace this with a discrete pair. And I've made them in the past. I'll show you how I do it. And they'll be thermally coupled just like this, but they'll be a lot more reliable. They should last a long time. Of course, how can I say reliable? Look how long this thing has lasted, and it still works right now. And it probably will work for some time to come, but we'll replace it anyway. This little insulation is probably, yep, it's just deteriorated completely. And those little diodes, those little thermal tracking diodes are under there. We'll have to clean that off, and there's a good chance that this stuff may have corroded the terminals a little bit too. So we'll need to clean that off, possibly put some more insulation on there, something a little better when we're done here. But we'll do that, get the capacitors replaced, and this thing should be good for another 30 or 40 or 50 years, hopefully. Well, you can tell this has had some heat on it because you can see all the flux on the board, the coating, and you can see where it's been real hot and it's turned kind of that amber or brown color. It really shows up in the camera even more than it does in real life here. But that'll definitely, we'll need to go over all these solder joints and touch them up. They don't look cracked, however, but I would still go over them. And the rest of these don't look too bad. Now these transistors here, might need some attention. I don't know. We'll re-grease them. Anything that's running real hot like this, we definitely, on this amp especially, Class A, you want to make sure all the heat sinks are properly thermally coupled to the transistors and so forth, so that you get the best heat transfer as possible. Okay, I'm ready to start replacing the components on this board that I'm going to replace. And most of the semiconductors are going to get replaced simply because of the amount of heat they've been exposed to. Although this amp doesn't look like it's been used for a whole lot, so some of these transistors would probably last a lot longer. But if this is going to go to someone else who's going to use it every day and, you know, connect it to their main system, I want this to be able to perform for many years with no problems. So that's why I've chosen to replace some of the semiconductors on this as well. You can see that these caps have definitely been subjected to some heat, and so we're going to replace those. This one's a special one. It's 160 volts at 22 microfarads. I don't know if you could see that there, but it's a non-polarized, and finding a non-polar capacitor of that size, electrolytic, is hard. So what I'm going to do is I'm going to use one of these film capacitors. These things are pretty much indestructible. Actually, there are some X-ray machines in the power supplies that these are used in the snubber boards, and these things are just, they can take a lot of punishment. So I'm going to put that in there. I'll probably end up mounting it on its side like this, and then, you know, run the leads down in here. This is kind of a known area on these amplifiers. These are your main rectifiers for the main power supply. And you can see there's 8 of them, and they're for your 2 channels. And those are what power these big 33,000 microfarad caps. And remember, in a Class AB amplifier, you only have a couple situations where these things are going to draw heavy current. Number one, when you first turn it on, you'll have a big inrush current as the caps charge. And then it'll kind of sit there at very low idle current. And even when you're playing the amplifier at normal listening volumes, you're really not drawing a whole lot of current through the diodes. But in a Class A amplifier, it's always running at high power, high current. So you have constant high current going through these diodes, you know, relative to what a Class AB would be doing, even if you're not listening to it at high volumes. And what that means is that these are going to get hot. Anytime there's a voltage drop across a component that has current flowing through it, that voltage drop is actually going to cause that device to dissipate power, as in the form of heat. So these are going to get hot, and that's exactly what happens to these. They're well rated for the amount of heat that they need to dissipate and the amount of current that they need to conduct. But when you see how they mounted them flush to the board like that. And that's kind of a mistake, because these are touching the board, and you can see how the board is discoloring from the heat. So what we're going to do is we're going to replace these with some heftier diodes, and we're going to mount those diodes just a little bit off the board. We're going to space them. Now you have to take some things into consideration. You can see these ceramic disc capacitors, and these are for the purpose of kind of snubbing out the switching noise of the transistor or of the diode. So anytime a diode goes from forward bias to reverse bias, there's a chance that you can have what's called switching noise. I won't get into big detail about that on this, but that noise can actually show up in the performance of the amplifier. So what these capacitors do is they help to suppress that. Now, the other thing that can help that is by using what's called a soft recovery diode. In other words, it's a diode that doesn't switch off abruptly. A Schottky diode is the total opposite of a soft recovery diode. It's a really fast recovery diode. And in this instance, you don't really want that. That soft recovery will help, again, suppress that switching noise. And then when you have this ceramic capacitor across the diode with it, that will further reduce that switching noise. So these are undoubtedly going to have a lower, slower recovery time by design. So that's what I'm going to use. And these diodes are a type P200D made by Diotech. And they are very tough. They're 200 volt diodes, and they're rated, I believe, at 20 amp forward current. And they're a soft recovery diode, relatively soft recovery. So they're absolutely perfect for this. They have really thick, heavy leads on them. And the lead is actually part of the heat dissipation of the diode. So if you want to run the diode at its maximum rating, it has to have the full lead length, because this is actually like a heat sink. So when we're going to bend these leads, we're going to kind of put a little S-curve in them. And that's going to help hold them in the board properly. And it's also going to give it a little extra lead length to help it dissipate the heat. And hopefully, the goal of this is to keep this board from discoloring and getting hot. I know I'm going on and on about this, but some of you who are really into doing this, this is a good tip to understand. All right, let's get started. So here is a list of the transistors that I'm going to use and what they're going to replace. And you can see I've sorted them out already, and I have all my capacitors that I need to replace, and I'm using all 105C capacitors. You can see like this one. These are Vichy, and you can still get these at Mauser's and DigiKey and places like that. They're still being manufactured, so that's a good thing. Because again, these are those axial leaded capacitors, and you could put a radial, but they're going to stick up, and it's going to be hard to get it in there to fit. So if you can find the correct ones, that's the best bet. So everything is 105. The audio path capacitors are film, as you can see. You have a few of those, and they're all very good. So everything should work well, and again, we shouldn't have to worry about thermal problems once we do this. And then I'm going to also replace these resistors, these pots, with high quality 15 turn 100 ohm pots. So we have really good adjustment on them, and should make it a lot easier to set your bias and offset. So what I'm doing now is I'm forming the leads for this. And you start out by bending it on the bending jig, like that. That's how I'm doing it. And I'm going to make it wider than the original one. See that? So you can see the bends on this one, and you see the bend on this one, and see how this one's wider. And then I have these old pliers, which I've had forever. These are wire forming pliers. See that? How they have that little curved part and then a straight part? And what that allows you to do is make these nice round bends in the wire. So what I'm going to do is I'm going to go over here, first of all, and I'm going to make this first bend around this way, like that. And let me get it pinched in there. So move them over like that. Then I'm going to come back on this end and pull it up like that. And that makes that nice little curve on there. And it gives you a little strain relief. And it also keeps the wires nice, that puts that nice bend, a straight bend in there. And then we can straighten it out a little bit. And when you're done, you should have something like that. And hopefully I got it close enough that it'll fit in there. So let me get these mounted up there, and you'll see how that's going to put a little bit of space and add a little bit of, hopefully keep the board from getting scorched. Okay, so here's the diodes. Much better now they're up off the board, so they can dissipate the heat better, and I shouldn't get a scorched board. Replace that capacitor there. This is kind of just glued onto the board with some adhesive and wired in there. It looks good. So now I'm working on this input pair. And this is a 2SA 798, and it's basically two PNP transistors in one case, so they're thermally coupled. So we're going to make one of these, and I'm going to use a KSA 992, which is these little transistors. We're going to put two of them together, and we're going to thermally couple them, and I'll show you how to do that in a minute. But the first thing we have to do is get a matched pair. So I have two of them in the transistor tester, and I'm going to go over here, and let's put transistor number 1, and we can see the curves, and you can see the spacing. I'm not even going to calculate the gain. And there's transistor 2, and you can see this one has a little bit higher gain than the other one. They're pretty close though, but they're not the same. That one's got higher gain, so number 2 has higher gain. So let's remove number 1. I'm going to try a different transistor. I'm just going to go down the list until I find one. Much closer, see that? Very close. So that's a little bit better. So let's see, let's swap out another one. I'm just going to go through till I find. Perfect. See that? There's 1, 2. Perfectly matched. And that's all there is to it. And if you leave it on for a little bit, you can see it creeps up a little bit as the temperature changes. Same thing should happen on this one. You can see it does. Very, very slight, but it does. So they're good. So that's a winner. We got a pair there, and I'll put these other ones away. And we should be good to go. Okay, here's a rough sketch of what we're doing. So the 2SA 798, the emitters are tied together, and they're connected to the center pin. This is a 5-pin device. And then the base and collector for each transistor is on either side. So you can't get it backwards. So you can put that transistor in either way, and it will still be wired properly, which is cool. So what we're going to do is we're going to take these two KSA 992s that are emitter collector base. We're going to face one of them this direction, and the other one we're going to face backwards. And that way, the two emitters will be tied together just like that. And then what we're going to do is we're going to put some heat shrink over that and some thermal glue. And I have this. There, I know everybody will ask what it is. There it is. And I'm going to put some glue inside there to make an encasement, and then I'll put this heat shrink over top of it. And then shrink it down and then let it harden. And then we'll have our own little thermally coupled dual transistor package. Okay, so I have the heat shrink in there. I have a little bit of glue inside there right now. And I just have this alligator clip holding the center leads together till I can tin them together. So I'm going to try to do this around the camera if I can with my shaky hands. Just like that. And those should be together, and they are. So now we have our own little transistor here. So now what I'm going to do is I'm going to take this heat shrink and I'm going to shrink it a little bit. Not a whole lot, just a little bit. Just like that. That's what I want. Now when that glue hardens, it'll be all thermally coupled. And I'll get my scissors here. We'll trim it off. Just like so. And there we go. One thermally coupled transistor. And you can just see the glue inside there a little bit. You see it? And it's all around the perimeter there. So that'll set up and we'll be good to go. And naturally, the first one I made, I connected backwards. What do I mean by that? So here it is. And if you look, the red one, which is the center pin, is the base. So I have the bases tied together instead of the emitters. So I had to make another one. Try this again. And this is what happens when you're filming video and not paying attention to what you're doing. Now, there we go. And that one, the red one, the center pin, is the emitter. So that's the correct one. This other one, well, it's no good. So, no problem. And there's our old and new transistors, and it should work just fine. And there it is, and yes, I did get the curve tracer out, and I matched another pair, so don't get worried about that. And see, here's what goes wrong with these things. You can see how these pins, these are not painted pins on this one. This is actual tarnish. And you can tell that because it rubs off with your fingers. You can kind of wipe it off. And what happens is that'll get up inside the transistor and it will actually cause these to get shot noise. And that's the failure mode of these. And almost all of them will do it eventually. So even though this one's working fine now, if we ran this long enough, over enough time, it would eventually do that. So this is kind of a way to avoid that by being proactive. All right, so that's it. I got all the new transistors and capacitors in. I replaced the pots and I set them to the same resistance that the old ones were. And these are, I think, 10 turns, so they're in good shape. Re-insulated those two diodes there. Put a little bit of silicone in between here. And everything is ready to go. So now all I need to do is just clean the back of the board off with some flux remover. And then I'm going to go ahead and work on the heat sink here. I want to get this cleaned off and get these remounted so that they can transfer the heat as best as possible. Okay, I'm cleaning up the heat sinks and re-greasing them and so forth. And I'm going to do this last one on camera so you can see the process. Because I get asked about this. I've done specific videos on this and everything, and people will still say, you never show me, you know. You never translates to, in this video, you didn't do every single thing that you did in every other video over and over again. So I can't help it. Sometimes you just have to kind of watch previous videos, and I do these things, but I digress. So the first thing you want to do is take these out. They're socketed, which is a good thing on this. And from all the heat, these letters will rub right off. You got to be really careful. These will probably just rub off just in me handling them. And it's just the way it is. I mean, these ones are still on, but they're faded. This one's faded. It's just the way it is. Remember, these things get really hot. But these are some of the best transistors money could buy for this thing. So there's really nothing you're going to buy that's going to be better. So if these are good, leave them alone. These Sankens are getting really hard to find. And they're good, like I said, they're super good quality. So I'm going to put this down. The first thing I'm going to do is I'm going to just roughly get the old heatsink grease off. I'm going to use a little bit of alcohol because alcohol is really good at breaking it down. I'm just going to clean that out. Then I want to get this really, really clean. So I'll take a little piece of either 600 or 1200 grit wet dry sandpaper, and I'll just very lightly go over this with the sandpaper just to buff all this off. Knock down any little burrs or high spots you might see. Just like that. Then I take a lint-free cloth and some acetone. Put some on the cloth. And then I just clean any of the swarf from the sanding or any of the crud, any oils. You want that all to be off of there. This has to really make good interface because of how hot these things run. You want it to work. You want it to be able to transfer the heat as efficiently as possible. Now for heatsink pads, I am not using the mica. And I'm not using the grease. I'm using something much better. I'm using these Bergquist interface pads. They're sticky on one side. They're thin. They have really good compression tolerance, but they will tear very easily. So you got to be really careful working with these. I'll open the camera up a little more here so you can see. So you can buy these. Usually DigiKey and Mauser will have these. You can also get them on things like eBay and places like that. A lot of electronic places will have them. They're not real cheap. They're not super expensive either. But you can look them up, and they have different ones that have different thermal transfer characteristics. This is probably one of the better ones. There are ones that are even more efficient than these, but the trade-off is the more thermally efficient they are, as far as transferring heat, the more delicate they are. These ones kind of have a good, combination. It's a good compromise. So you can see they're still like sill pads. They're a little bit thinner. And you have to put them on with the sticky side sticking up. Here, you put them on the transistor. If you try to stick this on over the holes on the heat sink, you'll never get it lined up in a million years. It'll just never line up. This is hard to do on camera here. Let's see if I have this. Looks like these pins are a little bit bent. Just like that. There we go. So you want it to be lined up like that. Then you're going to take your transistor and you're going to hold it. And you want to kind of tilt this down. You don't want this to face down. You want it to be facing up. And then you're just going to plug it right into the socket. If I can get it there. There. Just like that. And then we'll put our screws in. Just like so. And you don't have to crush this. You just want to snug it until it tightens up. And the socket will actually hold the screw from coming out. Once you just get a little bit tight. You don't want it so tight that it like buckles. And there you go. And that's it. That will last forever, and that will be so much better than just grease and mica pads. Grease and mica pads are not bad, but they're we're way beyond that in this day and age. So we'll take advantage of that technology. So there you go. That's done. I'll finish cleaning this up a little bit and then we'll put it all back together. Okay, and before the cover goes on, this is what it looks like. Turned out pretty good, I think. There we go. Okay, this board's all done and everything's ready to go on here. I just need to put a little dab of silicone in between here to kind of lock these down a little bit, and then everything's ready to go here. All the transistors. And you know, I've failed to mention something on the last clip, and that is when you replace these transistors, over half of them are going to have a different pin configuration than the original ones you're removing. In other words, for instance, when you look at this transistor here, this is a 2SA733. I'll give you this list, and if you look at it, it will show you the pinout of the replacement transistors I'm using. And even that can be wrong, because for instance, the KSC945s, they can have a collector in the center, or they could have the base in the center. This one that I'm using is emitter base collector. Some of them are emitter collector base. So what I'm trying to say is when you purchase transistors, the letters that come after the numbers, you know, like KSC945, there may be one that's a KSC945C, and that would indicate that the center pin is the collector. You have to beware of those things whenever you're getting replacement transistors. The pins could be different and often will be. So you have to rotate that transistor inside the socket there where you're putting it so that the correct pin lines up to the correct hole. And most of these small transistors all had to be, a lot of them had to be rotated in their sockets a little bit to get it right. So anyway, just wanted to make sure you're very aware of that. Always check the pins. Don't just blindly order what I have here and put it in the same way, because you might get ones by accident that are different pin out. Okay, we are all back together. And I did pull the relays and look, and they are perfect. They're in perfect condition. I expect them to be such. When they tie the two contacts together like that, what's going to happen is one contact is always just ever so slightly going to connect before the other. It's just kind of the way it works. And that actually helps with the pitting. If the one that comes in first is the one that takes all the hit, the other one that comes in is going to have a lot less current on it when it pulls in. And that usually means that these will last longer unless they tarnish. And these ones have not tarnished. They're all three, even the soft start, are in perfect condition. So we don't have to do anything with those. So what I'm going to do is I'm going to go and we're going to power this up on the current limiting. And we're going to check the voltages for each channel. So there's 4 power supplies that I want to check. If they all look good, then I think we're going to be safe, and the bulb's not coming on real bright. I think we'll be safe to go ahead and put full power on this, and then we can check our offset and our bias. Remember, we set the pots according to how they were, before I disturbed anything. So hopefully this will all work. So let's connect it up. You can see here, so I've got the plug here. Plug it into the current limited supply, turn on the buzzy transformer, turn on the meter, and I just kind of want to look at the voltage right now and see when we turn this on. Make sure this is turned on, and now let's turn on power. And yeah, the dim bulb is perfect, and both relays popped in. That's a good sign. You telling me I got this right the first time? Mark that one down on the calendar. All right, so let's go to ground, and let's go to first power supply is 18.9 volts. This should be negative 18.9, dead on. Other channel, plus 18.9, look at that. minus 18.9. They're dead on. And remember, they're only going to run at partial voltage because you have that big current limiting bulb running right now. So I'm going to let this cook for a few minutes to make sure nothing strange happens and that I don't smell any kind of cooking component smell. And if everything looks good, we're going to go over to full power. Okay, everything was going really well, so I'm going to go ahead. I have it plugged in to full power now, and I have it over here on the bench socket. And we're going to monitor the power. And let's see what we got here. And let's go. Very good. And we're idling at 2.47 amps. Let's look at our power supplies once again. I'm sure they're fine. 29, minus 29, minus 29, 29. Okay, so they're all good. All right, so let's change out the probes. Go to millivolts. And let's look at our DC offset. While that is running, and we'll see where we are. And I'm sure this is going to have to stabilize a little bit. This is going to have to run for 10 or 15 minutes. But let's go to ground, and let's go across channel 1. See if I can get hooked on. Yep. Okay, so we have about negative 12 millivolts of DC offset. So according to the instructions here, we want to adjust this pot, these two pots, which I have the amp facing this way right now. So these pots right here are what we're going to want to adjust. So they're right down in there. And I want to set that for 0 volts on this channel and then go over to that channel and check it. And again, this could change over time. And just so you see where I am, where we're going with this, it's this potentiometer right here that I'm touching. I don't know if you can see it right there, that blue one right there. All right, it's kind of dark in there, but give you the idea. And then the other one's right over here in this area. I don't know if the camera can see it or not. I don't know, but it's in there. And then the other one is in the middle, like right over in this area down in here. Okay, let's set our offset. Wrong way. Just barely have to touch it. So you could see how touchy this would be with a 1-turn pot. This is a 10-turn pot, and I'm just barely touching it. Okay, there we go. I mean, that's 0. Okay, so let's go over to the other channel and do the same thing. See if I trash my probe unconnecting it here. All right, that one's even closer. That's only at 8 millivolts. And of course, I slipped off of the pot there. There we go. Wow, less than 1 millivolt. I'll take that. Okay, so now let's look at the bias. And remember, we want about 850 millivolts per transistor. So you're only taking a sample of 1 transistor when we do this test. And that's what these test points are. They just go across one transistor pair there. And you times that by 2, and that's going to give you your 1.7 amps of idle current. That's pretty close. 841 millivolts. I'm not going to touch that. Now, if I did have to adjust it, that would be this pot right here. And that would just turn it up and down. But that's good. Let's see if we have to adjust the other side. Considering we've replaced components, that one's a little bit high. So let's turn that down. But considering I replaced so many components, this is actually pretty close. Let's see here. It's really hard to see down in there. I'm going to go into 845, something like that, just to give it a little leeway. There we go. That's good enough. Okay. And this is sitting right where it needs to be. Now, there is a little bit of question here where it says adjust VR1 for 80 millivolts between plus and minus output terminals. If you read some forums out there, some people say this is a typo. Other people say that they actually intentionally put an offset in there to move the switching point of the transistors. Well, I kind of have a hard time understanding that because this is a Class A amplifier. The transistors don't switch. They shift, they move up and down during, when there's a signal applied, but they never switch off. The transistors stay on throughout the entire cycle. And that's what makes it a Class A amplifier, really. So I kind of don't buy into that. And I think more in the lines of this is a typo, and therefore you want that midpoint set to 0 volts. So that's what I did. And again, if you know more about this than me, because you're somebody that's actually trained on this one or worked on these in a factory or something, let me know. I'm actually interested in that. So, okay. What I'm going to do now is I'm going to just let this thing run. It's already getting nice and toasty. These Class A's really get hot. But, wow, you can really feel it there. It's like uncomfortable on your fingers. Whew. Actually, the heat sink's upside down. Heat rises. So this is actually the worst case scenario. This should be the other way around. But you can't adjust it. You have to adjust it from the bottom. That's the only way you can reach the potentiometers on this thing. So the old ones, I think you could reach from either side. You can go through the grill on the top and kind of fish your way in, but it's still, you can't get on the test points. You got to be at the bottom. So it's the way it is, but this actually lets it heat up more quickly. So let me shut this off. I'm going to put the bottom cover on, flip it over, and we're going to just let it run for a little while and make sure everything stays stable. And if it does, we're going to do some tests on it. So as you can see now, we're all connected up and we are turned on and idling right now. So I'm just letting the amp warm up for a little bit. And I want to let this run for a good 15 minutes at least. And I'm going to let this hit its, whatever you want to call it, stabilized temperature. And I'm going to take a measurement of the heat sinks on both sides at what they're sitting at right now in idle. So in other words, there's no signal passing through the amp. It's just sitting idle right now with no signal. And we're going to take the temperature of the heat sinks, and then what we're going to do is, after I know that it's at its stabilized temperature, I'm going to run this amp at about 14 volts RMS, which is somewhere around the mid 20 watt. Remember, this is a 30 watt per channel amp. I'm going to run it at 20 some watts per channel. And I'm going to run it continuously for 10 minutes at that 20 some watts per channel. And I'm going to see what the temperature does on the heat sinks, because a very observant viewer commented, and so when I made the comment that the amplifier draws the same amount of current at full power to the speakers as when it's sitting idle. The current never changes, and I showed that. I think I showed you in the last video, when you run this thing, it's always drawing, 2.5, 3 amps of current, no matter whether you're driving it at full power to the speakers or no signal at all. So what he said was, if that's the case, the power has to be going somewhere. If it's going into the speakers, that means since you're not drawing more power from the mains, that would only stand to reason that the transistors would have to dissipate less heat, and therefore, when you drive this thing at full power, the heat sinks should actually get cooler instead of hotter. Very observant. So we're going to see that. That's what this experiment's going to be all about. So let's just let this roll for about 15 minutes. I'll come back, we'll take our measurements, and then we'll run it at full power, or close to, at least 25 watts per channel, something like that. Okay, this has been sitting a while now, so let's see what we have here. I don't know if I'm going to be able to get this all on camera or not, but we're around 132 degrees Fahrenheit, 133, something like that. And if I go over to this side, 135. So they're within 1 or 2 degrees Fahrenheit. Now, after it calibrated, now they're both almost perfect. Okay, so that's kind of where we are. Looking at the side here, yeah, it's about the same. Okay, so what I'm going to do now is I'm going to shut this back off. And we're going to start this up. So let's get the camera on the test equipment. Okay, so as you can see, I have the meter up here, and I'm going to set it, it's going to be about 14 volts, you're going to see, RMS. We're going to monitor the distortion, and we're just going to look at the signal on the right and left channel. So let me turn this on. And you can see 0.01% distortion, almost pushing full power. We're sitting at about 14 volts RMS. So what we're going to do now is I'm just going to let this cook like that. And I'm going to run this for probably about 10 minutes. And we're just going to see if the heat sink cools down. I'm not even going to touch it. I'm just going to let convection do its thing. And in theory, if our viewer is correct, we should see the temperature of the heat sinks drop. Place your bets. Well, this has been running steadily now for 17 minutes at this power. You can see nothing has moved. Nothing. The distortion is the same. The power is the same. The waveform looks the same. Nothing has changed. And let me go down and look at the heat sink. And if you look, it really hasn't changed at all. If anything, it's gone up on the, in the maximum, but at the center, right on the heat sink where we were measuring, it's still 133 Fahrenheit. Other channel, looking at it, I'm off camera, exactly the same, 133. So the temperature doesn't change at all, whether you're running it at full power or no power. One thing is for certain, this thing is definitely a stable amplifier. I mean, it just doesn't budge. So let's put a couple different signals through. Of course, we did a test on this earlier before I replaced the capacitors and things, but again, the components that were in there were in pretty good condition, so I really don't think we're going to make any difference in the performance. I think this amp was good and it still is good. Hopefully it'll last a long time. With all the new components and everything. Okay, doing the sweep test, you can see that the amplitude never changes with frequency. It's flat as a pancake. The meter doesn't change whatsoever. You don't see any breathing on the waveform. Of course, we can't go by the THD meter because the frequency's changing now because we're looking at a swept signal, but everything looks really good. If I go out of sweep mode and I go back up to my frequency and let's change it to, let's say, 10 kilohertz, and you can see can't even read it. It's, I mean, 0.002% THD. Look how clean the waveform looks. Let's go down to 20 hertz. And this can't read 20 hertz. It just doesn't work on it. But you can see everything looks good there. Although the two channels look 180 degrees out of phase. But that's, of course, because I'm using the chop mode on this. And it will do weird things like that. It has to do with the way the sweep works on this scope. And if I go up to, there we go, a little bit better. Now you can see they're in phase. But bottom line is, it is 50 hertz. That's 50 hertz there. And this is still jumping around a little bit, but not bad. There's 100 hertz. Let's see if chop will work now. Makes them look out of phase again. But you can see it's very good. Very, very good. And this is running it at almost max power. I'm at about 25 watts per channel. It's a 30 watt amp. So, not bad. Not bad at all. Okay, so we are ready to play some music. And I'm going to try something different right now. I'm actually working on another project that's going to end up being another video to do this. And it involves, well, this is the beginning of it, but this is not the final product. But anyway, what I want to try to do is capture the sound of the amplifier with its effects of the speaker load being on it as well. So I want to hear the output of the amplifier, but I don't really want all the background noise and garbage that you pick up through a microphone, because the microphone distorts the sound a lot. And of course, you're going to hear it through your speakers or through your headphones, but that's actually a good thing, because this is going to record it exactly as the amplifier is outputting it, or as close to it as I can. And then we're going to play it back, and then you can listen to it through your own listening device. And if you have a really good set of headphones or speakers or something, hopefully it'll reproduce what we're hearing, what I'm hearing on this end. Anyway, we'll see. Anyway, this is like I said, this is a beautiful amp, and I think this was really designed for jazz, classical, things like that. And, you know, I often wonder, what if Luciano Pavarotti was an audiophile?
Soundstage, why do you elude me? I've sacrificed all my beer money for thee, with terminals made of gold and capacitors made from unicorn dust, and kissed by Vestal virgins, a stylus made of hopeless diamond, yet like it I am still blue. All cable shine of copper, set free from the bonds of oxygen, so perfect, burning and directional, yet soundstage, your heart is still far from me. Oh, soundstage, why do you elude me? But alas, my ears may just be unworthy of thee.
That brought a tear to my eye. Truly, truly, it brought a tear to my eye. Anyway, I think that's it for this one, and I'm going to wrap this one up. And this amp, wow, I don't know if I'm not going to want to part with this one. It really, it does sound incredible. You can hear a difference. I kind of was skeptical about listening to these really inefficient Class A amplifiers, but there is something about it. They do have a characteristic sound that's kind of hard to put into words. You have to kind of listen to it. It just, the dynamics of it, you know, all kidding aside, the dynamics of these amps for what they are is pretty incredible. So I think this, I see why these were so coveted back in their day. So anyway, I do have the preamp to go with it. I think it's one of those C31s or something like that. We're going to clean that up and go over it, but that'll just probably be a one-part video. But until then, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon on the next video. Take care, everybody. Bye-bye.